deflection. A hydraulic jump is a phenomenon in fluid dynamics that happens when a fluid is moving over a surface at a high speed and suddenly slows down, increasing in height and decreasing in speed. A rapid rise in a turbulent and energy loss characterized in this shift. It is also frequently noticed in spillway, open waterway, and other hydraulic structures. Hydraulic engineers should pay close attention to this position and magnitude of a jump since they can have a big impact on how the structures are built and function. Next is objective. The objective of this experiment is to study the characteristics and behavior of a hydraulic jump, such as its location, size, and energy dissipation. This information can be used to predict the performance of hydraulic structures such as spillways, canals, and dams, and it is also important to design them for optimal efficiency and safety.
Basic concept of hydraulic jump. What is hydraulic jump? Basically, the hydraulic jump term refers to the rise in water level caused by the transformation from supercritical to the subcritical. When a hydraulic jump occurs, energy is lost due to turbulence flow. This is the example of hydraulic jump diagram. The uses of hydraulic jump. Hydraulic jump is used to dissipate or destroy the energy of water where it is not needed, otherwise it may cause damage to hydraulic structure. It may be used for mixing of certain chemicals. It may also be used as a discharge measuring device. Critical flow. A critical flow is one with the minimum specific energy. Critical flow is a flow that corresponds to critical depth, while for subcritical flow, when the depth of flow in channel exceeds the critical depth, the flow is subcritical or flowing or calm. The front number in this type of flow is less than 1. Supercritical flow. When the depth of flow in a channel is smaller than the critical depth, the flow is called as supercritical or shooting. The front number for this type is bigger than 1. The formula that we will use in hydraulic jump is the front number. To find the front number, we need to have the velocity over square root GD, which is G is gravitational constant and D is the depth of water flow. Next, we will find the specific energy. The specific energy that we will find by using the formula E equal to D plus V squared over 2G. Next, we will find the flow rate by using the formula Q equal to AV, and then we will also need to find the head loss. Lastly, we need to find the power losses. By using this formula, density times with G times with Q and times with head loss.
The first step to conduct the experiment is, first we must measure the width of the rectangular open channel by using the vernier caliper. Okay. The width of the rectangular open channel is 7.7 cm. Next, we measure the height of the sluice gate. Right now, the height of the sluice gate is 10 mm.
The sluice gate is positioned at the identified location in the rectangular open channel. Make sure that the sluice gate cannot move by screwing it tightly.
Next, we switch on the hydraulic bench, and then we open the valve to control the flow rate. And then we close the dump valve so that the water flow is steady. And lastly, we measure the flow rate by fixing the volume and set the time. The turret is positioned to create hydraulic jump in the center of rectangular open channel.
after the jump is stabilized, we measure the depth at the point of upstream and the point at the downstream using the dive gauge, and then we record the data.
Based on the experiment, we tabulate the result: height of tailgate, which is 0.06 meter, height of sluice gate, volume, time, D, the subcritical depth, D1, supercritical depth, D2, subcritical depth after sluice gate. First, we need to calculate the discharge or flow rate Q using the formula. Flow rate Q equal to volume V divided by T time. We take the sample calculation of height of sluice gate 0.07 meter. So the volume is 0.01 meters cube divided by 30.70 second, and we get the flow rate 0.00073 meter cube per second. After that, we need to calculate the velocity V1 and V2. We use the formula Q, which is the discharge or flow rate, equal to area multiplied with velocity. Same as Q flow rate equal to V width of the flow, D depth, V velocity. We rearrange and the formula become velocity equal to Q flow rate divided by V width of flow multiplied with depth. So we get the velocity 0.790 meter per second, and we need to calculate the second velocity, which we get 0.193 meter per second. After that, we need to find the Froude number, which first Froude number and second Froude number using the formula. Froude number equal to velocity divided by square root g gravity multiplied with d depth. For first Froude number, we get 2.303. The second Froude number, we get 0.278. We need to compare to generate hydraulic jump, which Froude number first should greater than or same as 1.7, or Froude number 2 should greater or same as 0.6. Based on our calculation, the first Froude number, which is 2.303, is bigger than 1.7. So the hydraulic jump generated. After that, we calculate the head loss using the formula. Head loss equal to open bracket depth for minus depth second depth minus first depth close bracket cube divided by 4 first depth multiplied with second depth, and we get the head loss 0.0215 meter. After that, we calculate the power loss using the formula. Rho, which the density of water, G is gravity, Q is flow rate or discharge that we calculate, HL is a head loss. So the density of water is 1000, gravity is 9.81, the flow rate is 0.00073, and we multiply it also with 0.0215, and we get the power loss. After that, we summarize our calculation with flow rate, first velocity, first Froude number, second velocity, second Froude number, head loss, power loss, and we state the hydraulic jump is generated or not generated.
Froude number is associated with the change of water depth and discharge in open channel. The result shows the simulation of the experiment by varying the head of the sluice gate, which is 0.07, 0.10, and 0.14 at two different flow rates. By observing the result, the upstream conjugate depth decreased as the downstream conjugate depth increased at constant discharge, whereas an increment in the downstream depth is obtained as discharge increase at constant upstream depth. The Froude number at the upstream depth boosts an upstream depth decline that can be attributed to the increase in flow velocity. On the other hand, an enhancement in the upstream Froude number is achieved by increasing the slow discharge at constant upstream depth. Next, for the error, variance error may occur, so the eyes must be perpendicular when reading the data. So, as a precaution, the head should not be measured near the joint or at a point where there is turbulence in the flow. The head measuring needles must be adjusted precisely. The tip of the needle must be just touching the water surface while taking observation.
For the conclusion, consequently, it can be said that hydraulic jump is the circumstances in which the channel water level rises. This occurs when supercritical flow, Froude number greater than 1, transition to subcritical flow, Froude number less than 1, and the supercritical flow encounters submerged object like a dam or a wheel, which causes the water to shoot upward. Hydraulic jump include energy losses in dam, channels, coring prevention downstream of a dam, and reversing water flow, and a high water level on the downstream side. Turbulence occurs which can cause the channel erosion and degradation is a drawback of hydraulics.